the last section is called related rates of change. A bit tricky, this one. This one will come up again when you practice integration, but we can have a really good look at it now. So worded questions that use the chain rule. That's what we're going to be looking at. Determine the rate of change. Rate is implicitly using the idea of time. So the rate of change, how something is changing over time, this means we're going to have something like this. We don't know exactly what it is yet, but we're talking about something changing over time. Derivatives are useful for this. So determine the rate of change of area. Aha. So area as time changes. So determine. So they want us to find this one out. Of a circle. Circle, okay, that might be important because we know some stuff about circles, don't we? That may be pi r squared or 2 pi r or something like that. Let's have a think about that one in a moment. When the radius is 3, okay, given that the radius is changing at a rate of 5 centimeters per second. So I know I'm handling this in a sort of blocky way, but let's just go through and get all the information. The radius is changing. So the radius, the radius is changing at a rate of centimeters. Those centimeters must be the radius per second. So look, rate, we have another rate here. So rate has the idea of time. We had it talking about area at the start of the question, and here it's talking about radius. Radius is changing at 5. Okay, so that is 5. Yeah. So rates, we're talking about time a lot. We have worded situations where we need to piece together what's happening. So let's just check these points here. The rate of change of area A. So we said when we hear rate, think about dt. So some sort of derivative of dt. The rate of change of the radius is r. Okay. Now, before we go any further, we've got dA dt, which we're supposed to work out because it says determine. We've also got, I'm not sure where to put it, but I've also got dr dt over here. If I write it like that, maybe that will sort of give you an idea if you think back to parametric differentiation. Is there a fraction that we can multiply by so that we could work this thing out? dr dt, we know what that is, that's 5. What would go there? Remember, the thing needs to cancel, so that must be dr. And there needs to be a for dA. So I've spotted this. I've been given that there. dA dr, what might that be connected to? Well, do you remember we were told that it was a circle? So do you know a formula that links area and radius for a circle? Well, you do, don't you? It's the pi r squared one. So dA dr, what you can do is if you differentiate it with respect to r, you get 2 pi r. You know, we kind of guessed these might be important. And that value you're going to use here. So it's like a chain rule. By using something about the area and the radius, which you kind of spot and use yourself, this tells you how area changes as radius changes. And by being given dr dt, you can use those indirectly to find how area changes over time. Quite a cool result. So it's about knowing what you're supposed to work out. I don't know if this animation is going to go. It's about knowing what you're supposed to work out and kind of sort of playing around with things and managing to get there. You'll get 2 pi r over here times by 5, which is 10 pi r. And if you've been keeping track of the information, we were told what's the rate of change at 3 centimeters. So we're meant to use that number there. So this question here, this is an example of a related rate. Okay, you get much better at these when you keep practicing them. Okay, you need to read carefully, get all of the information out. There's normally something about a shape, and there's the word rate appears many times. Let's do another example. Now, just visually looking at it, before I even do anything else, I can see a cylinder there. So I'm thinking already, volume pi r squared h. I'm thinking that might come in useful. Okay, maybe something about v and r. So dv dr seems like something I could work out. Let's keep going. It shows a right cylindrical metal rod, so there's nothing new there, which is expanding. Now, what is expanding? Expanding means the volume over time is getting bigger, so it must be some kind of positive number. After t seconds, the radius of the rod is x, so that's the same there, and the length's 5x, that's the same there. Doesn't seem to be anything new there. The cross section is that bit there. Cross section is increasing at a constant rate. So the area of the cross section, as time is going on, is increasing. Increasing means it's a positive number, okay? So 0.032. You don't actually need the plus sign there. So that has given me this one here. And can you see the units support what I've just done? A and t. So find dx dt. Dx dt. How on earth am I going to find this? Well, do I have other letters that can sort of help me chain this together? I feel like the DADT might be a good guess, but the A has to disappear. So maybe I'll write it like this. If the A's cancel, that means there would need to be an A there, and there would need to be an X. So is there any way we can make some kind of equation that has A, the area of this circle, and X? Well, it's pi r squared again, isn't it? So the area equals pi r squared. R is x in this case. So dA dx equals 2 pi x. Now that doesn't say dA dx, that says dx dA, so you need to turn it upside down. Dx dA equals 1 over 2 pi x. So there you go, 1 over 2 pi x. dA dt, you know that because it was given to you in the question, times 0.032. So that's what this one equals. When the rod is 2 centimeters, when the radius is 2 centimeters. So the final thing you do is you make that number there a 2. And that's how we answer this question here. So just before we go any further, why don't we just have a quick look at that one? So a neat diversion. Okay, so 0.032 times 1 over this. Put the number in, we should get a very small number here, 0.00254, and so on. Now you might. Okay, so we did this previous question here. So let's talk about part B. So part B said, find the rate of increase. So the rate of increase of the volume. So you know it's about dV. Rate tells you it's about time. So it wants this one here. Okay. Now, what information do we have available to us to get this? Well, we need something with dt in the denominator there, and we need something with dv. Now, this was about area. Okay. This is dx dt. Well, that could work. That might work because we just found that in the previous section. So if we had dx dt, what would this part need to be? That would need to be dx for those to cancel to get dv over dt. So is there any way we can link v and x together? Well, you might remember we talked before about it was sort of suspicious that they had this here. They had a well-known object. Well, pi r squared, but instead of pi r squared, pi x squared in this case, it's going to give you the area, and then multiply by 5x is going to give you the volume. So 5 pi x cubed, if I do cross-sectional area in terms of x multiplied by 5x, if I differentiate that, that's going to give me this one here. So dv over dx equals 15 pi x squared. And dx dt, we found it out already in this format, actually. So we would, well, I suppose we could write 15 pi x squared multiplied by, and I would use this exact form here because it's going to be more accurate. Okay, that was this one. And if we do that, we get an answer for that one. Oh yeah, we did. Sorry, we got this x here, so that won't give you an answer yet. So what we had to do, yeah, look, there we go. We'd use that result. So that will then give you a numerical answer. You could even simplify this a little bit before you type it in by cancelling the pi's and things like this. You should get 0.48. So that tells you dv dt. So the part A section was used in part B, something we always need to be on the lookout. It doesn't always work that way, but that is something that is often done. Let's do one more. So pause the video and have a go here. So dvdx, for this one, for just 1 mark, we could make an equation linking v and x, because look, x times x times x cubed gives the volume of a cube. Okay, dv over dx equals 3x squared. It did say show that, so they probably want to see the original equation. Yeah. Given that the volume is increasing at a rate, so that means that one there is dv dt. We've also just worked this one out, so maybe we have to do something with these together. Who knows? Find dx dt. Well, let's write out dx dt. So there has to be an x there and a t there. Do these work? Vt. So dv dt, we could use that one there. If we use dv dt there, we'd need another dv here, wouldn't we? Dx dv. Well, you've almost got that. Dv dx is that. So dx dv is the reciprocal, 1 over 3x squared. So 1 over 3x squared is that one there, dx dv, yeah. Dv dt is this number that we were told here. When x equals 4, not 4, 8. So you put x equals 8 in there, solve that one, should give you your answer. Yeah. Find the rate of increase of the total surface area. Total surface area, that means this face and that face and that face, all of the faces. So the area, I'm using A for total surface area here, is going to be equal to this square, that's x squared, and there will be 6 of them. So there will be 6x squareds. Find the rate of increase. Find the rate of increase. So they're talking about, let's use this space over here, rate of increase of the surface area. They're talking about dA dt, aren't they? That's what they're doing. Well, let's finish with this one. What would this give us? This would give us dA dx equals 12x. So I think we want to go for dA dx. There needs to be a t in the denominator, so that must be an x. Dx dt, hopefully we've got that, or we can work that out. That was this one here. That was our answer to part B, is used for C. So you've got that one there, and then you've got the 12x there. Make x equal to 8, give you your answer. Okay. That's the question. So, yeah, practice plenty and plenty of these ones here. The only ones I'd say maybe that are kind of missing from what we're talking about here, and this will come up more when you do integration, is you'll also just need to be aware of proportional statements. So we might say something like the rate of change of volume is proportional to, let's say something like T. And you might remember from your GCSE knowledge that you can do something like this. Okay, so the only thing that you haven't seen so far that you might see a little bit more in integration is statements about proportionality may turn into equations as well. And you're at the end of the chapter. That is 9J. So well done for making it through. Now you need to get ready for integration. Integration is a bigger topic still. So best of luck. Keep practicing. Differentiation. See you next time.